sharing my screen. All right. So I need my anyway. So what is the conclusion of the last couple of lectures? The conclusion is we have for the whole airplane, we have the lift coefficient is linear in the angle of attack, a constant plus some constant times the angle of attack. So this is the lift coefficient for the entire airplane.
Sir, we cannot see any writing. Oh, just kidding.
Oh yeah, all right. Thank you. So this is the lift, how the lift coefficient for the entire airplane looks like. Just a line, varies linearly with the angle of attack. And the same for the moment. The moment probably is more critical. CMCG is also a constant plus another constant times the angle of attack. And last time we discussed that we wanted to look like this, right? Positive CM naught and the slope, which is CM alpha, should be negative. And I'm reminding you that these four constants, right? Two constants to define the line of the lift, two other constants to define the line of the moment, right? Each one of these constants, it has two contributions, wing and tail, wing and tail, wing and tail, wing and tail, at least, right? There are other contributions that we neglected throughout this course, but at least we get the wing and tail contributions. Any questions so far? So for example, for the CM note, there is the wing and tail contribution. So the wing contribution, if you remember from last time, that was something like CM aerodynamic center wing plus CL naught wing times the difference XCG minus X aerodynamic center wing over C bar. And there is the tail contribution, which was something like eta tail VH CL alpha tail epsilon naught plus I wing minus I tail. Also the CM alpha, it has two contributions. The wing contribution, which was CL alpha wing times the difference CG minus aerodynamic center wing over C bar. And we have the tail contribution, which is negative eta tail VH CL alpha tail 1 minus D epsilon by the alpha. All right, so we derived these equations last time. What do we need from this equation? What are the types of problems that we can encounter, whether it's in homework exam or in our life when you work as an aeronautical engineer in some airplane manufacturer company or a research company or something? Well, there are three types of questions. First, to derive these equations, we derive them for the conventional configuration, like a wing and tail behind the wing. But there are other configurations, right? There are other configurations like simply canard configuration, which is a wing, and instead of having the tail behind the wing, we have the tail in front of the wing, and we call it canard in this case. So this is the canard configuration. And in fact, I'm going to release the homework today and right after the lecture, and you will have to derive, you will need to derive similar equations for the wing and canard configuration, right? The contribution of wing and canard in this case. And you will exactly follow the steps that we had last lecture, just replace the tail by a canard in front of the wing, and that's it. So the first question is to derive the equations. Fine, we derived them last lecture. The second is, once we have the equation, we need to get these numbers. I need to get this number for the CM naught and CM alpha. We need to plug numbers into these equations to get the airplane lift and moment characteristics. And the third is, once we have the characteristics, what do we do with them? What can we infer about the airplane stability and control characteristics from these two lines, which means from these four numbers, right? So today, so last time we covered the derivation. Today we're going to have a couple of problems on these two things, which is first, let's plug some numbers and get these CM naught, CM alpha kind of thing. So this is actually, I'm going to release this lecture summary afterwards, as usual. So let me take from it here. This is problem 2.2 in Nelson. You don't need to have it. You don't need to have the book anyway, but it's a good book to have. So it's giving us a general aviation airplane, like one of the small and light airplanes that if you want to get your license, you will have to, fly them first. You will learn your flight lessons on one of these airplanes. Here is the airplane, and it's given to scale. And here are the characteristics: XCG, area of the wing. And please, if you have any question, do not hesitate. I understand you may have not studied anything. That's okay for now. So you may not know what is S. So please ask. B is the span of the wing, and here is the chord. Area of the tail, L tail is the tail moment to arm. So we're given some characteristics. We're also given the wing airfoil characteristics. When we say airfoil, we already know automatically that this is two-dimensional, right? And we're given the tail airfoil characteristics. All right, so we're given a bunch of things. And what is required? Here is the requirement. Determine the wing and tail contributions to the CM versus alpha curve. This CM versus alpha is a line, as like any line, it's defined by two constants. Here are the two constants, CM naught and CM alpha. Each one of these constants has two contributions from wing and tail. So we need to determine these four numbers and add them together to get, respectively, to get the two numbers CM naught and CM alpha. Questions about what do we need to do? We'll see how to do it, but we need first to know what do we need to do. Any questions so far? So simply, I'm gonna try to use all these givens to apply into these equations directly, and that's it. So for example, first of all, the wing contribution in red to this constant CM naught of the airplane, here is the equation for it. The first term is CM aerodynamic center wing. Well, here is the wing, here is the CM aerodynamic center wing. So I have this. Second, CL naught wing. Okay, how can I get the CL naught? So aside from the CL naught, there is CG and there is aerodynamic center, and both are given. Here's the CG, and X aerodynamic center wing is quarter chord. And even if it's not given, I already know that it's quarter chord. I'm gonna always assume it to be quarter chord if it's not given. So actually, in this red line, everything is directly given. I'm done. I'm gonna do it in a second. But CL naught wing is not given. How can I get CL naught for any section, for any wing, for any surface, whether it's wing or tail? So let's see, how can I get, so this is now for the wing. So actually, let's do it for any surface. So I'm gonna do it for any surface. This is the lift coefficient. It looks like that of the airplane. So for 2D airfoil, similar to 3D wing, actually similar to the entire airplane, this is the lift characteristics. Fine. All right. Yeah, we'll do it. Oopsies. I want to move this to the right a little bit. This is CL. All right. So this distance is CL, what we call the CL naught, right? And this point is what we call alpha zero lift. The name is very expressive. The angle of attack at which the lift is zero. This is typically negative for cambered airfoils. All right. And the slope of that curve is what? What is the slope? What do we call the slope? Anyone can guess?
CL alpha.
Exactly. This is the CL alpha. So the slope is the CL alpha, the slope of the lift curve, which is 2 pi for a 2-dimensional airfoil, and for a 3-dimensional airfoil, we know how to get it, and we're gonna do some training on it now. So from this geometry, can you give me CL naught in terms of the rest? Yes, simply, I mean, I know tan this angle is CL naught over this distance, which is the alpha zero lift, right? So CL naught is tan of the angle. Tan the angle is the slope times alpha zero lift, and I need it as a distance, so it's typically negative. I just need the absolute value, and this is a universal relation. Use it whenever needed. All right, any question about that? So I'm gonna apply for the wing now. I need CL naught wing because I'm here. So let's see, I need alpha zero lift for the wing, and it's indeed for the wing airfoil characteristics. It's given as -5 degrees. Great. I need the slope of the lift curve of the wing, CL alpha wing. Well, I'm given that, but it's for the airfoil characteristics. So I'm given the 2D version of it. So actually it's C little l, not large l. So this is the 2D CL alpha, and I need this the 3D CL alpha. Anyone remembers how to get that? So always, if you're given 2-dimensional CL alpha and you want the 3-dimensional CL alpha, this is lecture 1, what we called the extended lifting line theory. It gives you the 3-dimensional CL alpha as pi aspect ratio over square root 1 plus kappa squared. So I think I'm missing something, right? This is, let's see. I guess there is one in front of it. Yeah, you can see this. Just gonna get lecture 1 also at our disposal whenever we need it. So let me share again. So this was lecture 1. Here is the CL alpha extended lifting line theory. CL alpha 3D is pi aspect ratio over this thing. All right. There is another one here. All right. And this is for anything. Like I can use it exactly the same for the wing. Let's use it exactly the same for the wing.
Professor.
Yes.
Could you just real quick go over again what CL alpha and C little l alpha is?
Sure. C little l alpha. Sometimes we give it the name A naught. This is the 2-dimensional for the 2-dimensional airfoil. So it says, look at this. This is wing airfoil characteristics. It's not just wing characteristics. So this is for 2-dimensional. The C large L alpha, this is 3-dimensional. And you can always get one from the other if you know the aspect ratio. And here is how we do it now. So the CL alpha, this is a generic relation. I'm going to have wing, wing, wing. All right. So what is kappa? Well, kappa is actually pi aspect ratio over A naught. A naught is actually the, sometimes they call it A naught, sometimes they call it the CL little alpha. So we're going to use them interchangeably. So you'll find both notations in books. Okay. So, and again, this is wing, wing, wing. And what is the aspect ratio? Well, the aspect ratio is simply B squared over S. Right? So I have the span, I have the area. Of course, these are for the wing. So I'm gonna do 33.4 squared over the area. The area is 184. So I got the aspect ratio wing, 6.6, I guess. No? The aspect ratio is 6.06. This is the aspect ratio of the wing. I plug it here. And I have the CL alpha, two-dimensional. It's 0.097. This guy is 0.097. This is per degree. And this is something that we need to discuss, folks. The lift coefficient and moment coefficient are dimensionless and unitless, right? This is the main point of writing coefficients. But CM alpha or CL alpha is a slope. It's something like CL over alpha or CM over alpha. So they are coefficients divided by an angle. So they have units. The units is 1 over an angle, 1 over degree or 1 over radians, all right? So this is why CL alpha here is given as 1 over degree. So I'm gonna multiply it by 180 over pi to convert it to per radians, all right? So from this, I'm gonna get my K kappa wing or K wing. I put it here and I put aspect ratio there. So it gives me immediately the CL alpha wing, three-dimensional. And this is 4.2 per radians. Any question about that? Any questions, folks? So always in the back of your mind, whenever you have the two-dimensional lift curve slope, you can get the three-dimensional only if you have the aspect ratio. You just need the aspect ratio, simply. Okay. And the equation is given. I mean, you don't need to memorize anything. The equation will be given in your cheat sheet. We can because we're gonna do something about the tail. Let's repeat this process again for the tail. So I'm gonna use the exact same equation. So CL alpha tail is pi aspect ratio of the tail over 1 plus square root 1 plus kappa squared. This is kappa tail, where kappa tail is the exact same thing, pi aspect ratio of the tail over A naught or CL alpha tail, right? This was CL alpha wing. And the aspect ratio of the tail is B squared of the tail over S tail, right? Do you have everything? Almost. Let's see. So area tail, S tail. Here's S tail, 43. So this guy is 43 feet square. CL alpha tail, the little, this is the tail airfoil characteristics. Here is the tail airfoil characteristics. I have CL alpha tail, 0.1 per degree. So I'm gonna put this 0.1, again multiplying 180 over pi to be per radians. I just need the aspect ratio, of course. So I have the S tail. I need the B tail, the span of the tail. Let's see. So we're given, of course, the span of the wing. We're given area tail, L tail, but we're not given the span of the tail. Okay. But remember that we're given, what is the span of the tail? This is the span of the tail, B tail. And of course, this is span of the wing. This is B of the wing, which is simply B because it's for the entire airplane as well. So, and this is to scale. So I'm given the actual B is 33 feet. And I can go and measure on by using your ruler. And yes, don't laugh. You're going to use rulers sometime in this course. You're going to use your ruler to measure this distance. Say it's 5 centimeters or something. So you have the scale. Use this scale to get B tail. Any question about that? When you do that, you find that B tail is around what, 13 feet, I guess. Yeah, 13 feet. Questions?
Where was this? Sorry, Professor, where was the scale given for B tail?
You are given the actual B for the wing here. It's 33 feet. Okay, and I'm gonna measure this by my ruler. So say it's 5 centimeters or something. So by knowing the actual B and the measured B, you get the scale of the entire drawing. Once you have the scale, you go and measure BT using your ruler, multiplying by the scale that you got. So you get the actual B tail. On exams, no. On homework, yes.
I'm a little confused. Is there a given ratio of span to span tail?
No. There is no given ratio, but the drawing is given. This 3D, this drawing is given, and it is to scale. So you are given the actual B is 33 feet, and you will use your ruler to measure B from the drawing. You can divide them, these two numbers, by to get that scale. Once you have that scale of the drawing, I can get any distance that I like from the drawing.
Oh,
Why? Yeah.
Oh, I get it now. Thank you, Professor.
You're welcome. All right. So I think, okay, we're done with it, right? So B tail now is I have B tail is, it's 13. So this is 13 squared. So I got the aspect ratio of the tail. Must be always smaller than aspect ratio of the wing because the tail is shorter. So this is 3.93. And whenever you have like 3D surfaces, wing-like surfaces, whether it's the wing or the tail, one has an aspect ratio 6 and one has an aspect ratio, smaller aspect ratio, like 3.9 or 4. So do you expect this blue thing, which has a smaller aspect ratio, do you expect it to have smaller or larger CL alpha? So I use this aspect ratio, I got this CL alpha. I'm gonna do it exactly the same now. I'm gonna use this aspect ratio, I'm gonna substitute it here and there, substitute this kappa here to get the CL alpha tail naturally without any speculation, but just to check myself and to make sure that I'm adhering to the physics. Whenever I have a smaller aspect ratio, do you expect a smaller or larger CL alpha? Let's think together. Don't feel shy.
Smaller one.
Exactly, smaller one. Remember, always remember that the largest CL alpha is the 2 pi, and this is for the infinite wing. Once you make it finite, it becomes smaller than this limit of 2 pi, and the shorter you cut, the smaller CL alpha you get. All right. So I expect this to be smaller than 4.2. This is like a check for yourself on the homework and exam or something. Here, CL alpha tail is 3.65 per radians. So we got the three-dimensional CL alphas from the two-dimensional ones. We're done. Let's go back to our goal, because don't lose track. Yes, the tail span here in this problem is the only thing that was found using the scale, right? It was not given, so it's the only thing that we got out of the picture, out of the drawing. All right, so we got our CL alpha, the three-dimensional. I was here, everything was waiting. Actually, everything was ready. Same aerodynamic center wing, the X's, CL0 wing was waiting, and CL0 for any surface depending on its CL alpha, and I got the CL alpha. So we're ready. So let's get the CL naught wing is my CL alpha wing times alpha 0 left wing.
I'm sorry, Professor. Was the reference area of the tail also found by
It
the
was
scale?
it was given. It was given.
Oh, it was given? Okay.
Yeah, and if it wasn't, I would have got it the same way. But luckily, it was given.
Okay, thank you, thank you.
You're welcome. So CL alpha wing, here it is. It's 4.2 per radians, and just move the units with you for everything to be clear. Times alpha 0 left wing. Here is alpha 0 left for the wing. It's -5 degrees, and we use the absolute value, so it's 5 degrees. And once you move everything with the units with you, you realize, oh yeah, this is now per radians and this is degree. I need to be consistent, so I need to convert one to the other. So I'm going to multiply this by pi over 180. Now this is radians. So I am multiplying per radians times radians, so the result has no unit. All right. This is the CL naught, which is 0.37 for the wing. So we got the CL naught wing. I got it. Why? Because I have this equation that was waiting for me. What does this equation represent? Well, it's the wing contribution to this constant in the moment characteristics of the airplane. Okay, so let's try to keep track of the goal, not to get drawn in the details, because we have too many details. So I'm going to copy this equation now. So, and this term has a name, right? What is the name? It's the wing contribution. When I say wing contribution in this course, I do like this. Delta wing of what? Of Cm naught of the entire airplane. This is the wing contribution, right? Let's simply substitute. It's just direct substitution. So Cm aerodynamic center wing was given. Here is Cm aerodynamic center wing, -0.16116. Plus CL naught wing, I just got it, 0.37. Times the difference of the x's, and both are given. XCG was 0.295. X aerodynamic center for the wing is quarter chord, and if it's not given, I'm going to always assume it at quarter chord. So this is 0.295 minus quarter. So we got this number. This is -0.0. Oopsies. -0.099. Remember the Cm naught for the entire airplane. We got the wing contribution for the Cm naught of the entire airplane. Cm naught is this distance, right? For the Cm alpha curve, the line. Remember, we want this Cm naught to be positive or negative. Anyone remembers from last time? So this drawing has a positive or negative Cm naught? Positive, exactly, Eric. So we want it to be positive for a good balance for the airplane. And as you can see, the wing contribution, the wing provides a negative contribution. So it's not favorable, and hopefully the tail will provide the desired contribution and should be strong enough to outweigh the wing contribution. Okay. We are still with the wing. Since we did many things with the wing, let's finish the wing stuff. So let's get this, the wing contribution for Cm alpha, and I'm going to write it similarly. So this is the wing contribution, delta wing for Cm alpha, the other constant. This is what I'm going to copy it from there. Here it is. And all these equations are given just if you for you not to be intimidated. Here are these contributions: delta wing Cm naught, delta wing Cm alpha, delta tail Cm naught, delta tail Cm alpha. So you just copy them from your cheat sheet. Okay. So this is delta wing Cm alpha, and When everything is ready, I'm going to simply substitute the lift curve slope. I already got it. It was 4.2 per radians times the difference in the x's. This was 0.295 minus quarter. This is exactly the same. So I got the CM alpha thing. This 0.19. Does it have a unit or it's unitless? Should I write something here or I'm done? I just box it like this.
It should be unitless, right?
So let's see, what is that? This is the wing contribution for something. What is this thing? It's CM alpha. So CM alpha, does it have a unit or it's unitless? Yes, exactly, per radians. And then you can see it from here. So these things are non-dimensional and no unit. This is per radians, so the per radians will be transferred as is. So this is really per radians, all right? And I'm going to ask you, so this is CM alpha for the entire airplane. I don't have a subscript here, all right? But for the entire airplane, a part of it comes from the wing and a part comes from the tail. CM alpha is the slope of this line. Do we want it to be positive or negative?
Negative.
Exactly. This is like if you're gonna take only one take-home message out of this course, it is this take-home message. CM alpha for the entire airplane must be negative. And why? It's for stability. If it's positive, the airplane will be unstable. Okay. So the CM alpha for the entire airplane must be negative. Unfortunately, the wing is providing a positive contribution, which is unfavorable. So the wing is destabilizing. So again, hopefully the tail will adjust that. All right. Questions? So we got the wing contribution. Let's move to the tail. Let's get the blue stuff. So I'm gonna copy this and see if I have all the details or not. So what is zeta tail? This is what we discussed last time. This is a ratio between the dynamic pressure on the tail to that of the wing. It's typically between 0.9 to 1. So if you're not given it, you're free to assume it between 0.9 to 1. I'm going to assume it to be 0.9 here. What is VH? VH is a ratio. It's S tail, L tail over SC bar. Every single one of these are given. CL alpha tail, we got it already when we were getting the CL alphas. I wing is given. Here is the wing incidence angle. How are you going to place the wing on the airplane? At what angle? I tail is similar. How are you going to place the tail at what angle? So we're given these. So pretty much we have everything here, probably except this epsilon node. Anybody remembers what is epsilon? What is that?
It's the downwash angle.
Exactly, very good. Epsilon in general is the downwash angle. Epsilon is the downwash. And why do we have a downwash at the tail? Well, it's because of the tip vortices on the wing. So this is why the lifting line theory gives this as function of the wing lift characteristics. So it's 2CL wing over pi aspect ratio of the wing, even though this is at the tail. So the downwash at the tail is just related to the lift on the wing and the wing characteristics. And like anything in this course, we like to distribute it as a constant plus a constant times alpha. So the epsilon naught is the constant part. This is easy. This is 2CL naught wing over pi aspect ratio. And d epsilon by d alpha is 2CL alpha wing over pi aspect ratio, right? So here I'm going to substitute. This is 2CL naught wing. We got it from above, was 0.37 by aspect ratio wing, 6.06. You got a number. And the same here. This is 2. CL alpha wing was 4.2 per radians. In these two relations, we need to stick to per radians divided by pi 6.06. This is the aspect ratio. So we got this as a number, 0.44. And you can see here, epsilon is a downwash angle. So it's an angle, has units of angle. And here I'm dividing by alpha, which is another angle, so they cancel out. So the epsilon by the alpha, it has no unit. I'm done. Epsilon naught is an angle, like I said, epsilon is an angle. So this actually has the units of an angle. So we got it from here directly, of course, in the units of radians. So we got some number in the units of radians. And if I want to just visualize it to myself, I'm gonna multiply by 180 over pi to convert it to degree to myself. If this is the case, it will be 2.2 degrees. So I got epsilon naught, I got the epsilon by alpha if I ever need it. So let's go here and complete. So I'm ready. I'm gonna take this. So what should I call this? What's that? Any suggestion? Let's see. What is that? So it's CM naught for the entire airplane. And this is the part that is coming from the tail. So how do we denote it? CM naught for the entire airplane, and this is the part that is coming from the tail. And I'm gonna do direct substitution. Eta is 0.9. Like I said, VH is S tail, L tail over SC bar. So let's get these. S tail is 43, L tail is 16. This is 184, and this is 5.7. So this ratio is 43 times 16, 184, 5.7. This ratio is the VH times CL alpha tail. We got CL alpha tail above was 3.65. And this is per radians, trying to move the units with me, times a collection of these angles. Epsilon naught was 2.2 degrees. I just got it here. I wing was 1 degree. I tail was -1 degree, I guess. Let's go and check these. Here's I wing is 1 degree. I tail is -1 degree. So I'm adding degree to degree to degree. So that's good. I'm consistent in the addition. So the result here is in degree, right?
Professor?
Yes, please.
Can you just quickly re-go over how you found the eta sub t term? I just missed
yeah,
that part.
no, that you didn't miss it actually. So eta sub t is not given, and I'm saying that we typically assume it in the range between 0.9 to 1. So this is assumed here. Right. So here in this problem, I assumed it to be 0.9. If it's not given, typically it should be given. If it's not, I'm going to assume it in this range. So, so in the addition, I was consistent, but now I'm multiplying something per radians times degree. So I need to be consistent in the multiplication. I'm gonna, oopsies, okay. I'm gonna convert this. I'm gonna multiply here by pi over 180, so that this thing is in radians, and I'm multiplying per radians times radians. So I will get something of no dimension, because this is CM is 0 is of no dimension. So carry out this computation. The result is we want CM naught for the entire airplane to be what? Positive or negative?
Positive.
Positive. The wing was negative. I hope that the tail is positive enough. So the tail here is 0.16. The wing was almost negative 0.1 or something. So this is positive and strong enough to outweigh the wing contribution. So the other thing here, so these are the two constants I'm interested in, right? For the CM versus alpha, like any line, it's defined by two constants. And each one of these two constants has two parts, one coming from the wing and one coming from the tail. So I got this part, which is the tail contribution to CM naught. Now I'm going to compute this part and it will be done. And please tell me how to denote this part, how we call it. Any suggestion? What should I call this part?
Delta TUCM alpha.
Exactly, thank you. And everything is given. I'm gonna do direct substitution. This is 0.9 eta tail assumed. The VH is a ratio. I'm gonna take this whole ratio, right? And I'm gonna repeat it again down here. CL alpha tail, I'm gonna do it again, 3.65 per radians. 1 minus the epsilon by the alpha. I got the epsilon by the alpha was already 0.44 here. So you can see here, eta is of no unit. This is a ratio of length, or sorry, volumes, right? Area times the length, area times the length. So this is a ratio of volumes, no unit. This is also no unit. Here, the unit is per radian, so it will carry out with me. So the entire thing will be in per radians, because this is CM over alpha, right? So the result is, do you expect a positive number or a negative number here?
Negative.
Exactly, so this is negative 1.21 and it's per radians. We want CM alpha for the entire airplane to be negative for stability. And the wing was providing a positive contribution, so it's destabilizing. This is 0.19. The tail is providing stabilizing, and it's large enough to outweigh the wing contribution. So we got the four numbers. We got the four numbers. So for, yes.
Sorry, would the 0.16 number be unitless or also per radians?
No, that's a good question. This is no unit. Why? Because this is simply CM. It's not CM divided by an angle or something, right?
Oh, okay, thank you so much.
You're welcome. So, so the wing, so here is the summary. The summary. The wing contribution to the CM of the entire CG of the airplane, something plus something times alpha. This was negative 0.099 plus 0.19 times alpha. While that of the tail, delta tail of the CM of the entire airplane is again something plus something times alpha. This is the 0.16, negative 1.21 times alpha, right? And for the total airplane, I simply add them. I simply add them, right? So this is alpha, this is CM. Let's sketch or the wing contribution. This is, say, the wing contribution. It's CM naught is negative, so I go down this distance and I have a positive slope. It's weak though, so it's something like this. This is the wing contribution. This is the line. On its own, it's not good for balance. It's unstable. You can't fly it alone. This particular wing, I mean, you can design a fly an only wing that's stable, but this needs an art. The tail was, here's the tail. This is the CM node value 0.16, and we have a very strong slope, negative. This is the tail. And this is wing. And we simply add these two lines to get the entire airplane. So we add the two CM naught to get, this is the CM naught of the entire airplane. And the slope, you add the two slopes, so you get something like that. So this is the total. Questions?
So is it just like a vector addition, basically?
I'm sorry, it's what?
Is this just like a vector addition, basically?
It's not vectors, it's we're adding the respective constants. So we're adding the CM notes together to get the CM note for the entire airplane. We're adding the CM alphas together to get the CM alphas for the entire airplane. All right. Questions?
Professor, how do we get the line of total?
The total?
Yeah.
You add the two lines.
Oh,
You add the two lines.
Oh,
So I added the two constants to get this constant, CM note for the entire airplane, and I added the two slopes.
okay. And by the way, so in the problem it says the LT is in feet square, so it should be in feet, right?
I'm sorry, I didn't get this question. What's the question again? Can you, yeah, go ahead.
In the question, so LT is 16 feet, but
yes, LT 16 feet, okay.
So it should be 16 feet, right?
I used something else. Let's see. It's 16, yeah, 16 feet. Yes.
Yeah, but you said it's like universe, but depending on
no, it's the VH is, so VH is S tail L tail over SC bar. It's a ratio of area times the length, area times the length. It's a ratio of volumes. This VH, the whole thing. L tail alone is unit, but
but what I'm saying, like the problem itself is it shows the LT is in feet square, 9 feet.
Yeah, sure. LT is 16 feet. Yes. Oh, yeah. Thank you. Yeah. Okay, I didn't. Yeah, this is not all right. So he's saying that this shouldn't be feet square. This is feet. Yes, you're totally correct. Thank you. Any other question? So if you want to add them, so CMCG, simply we add them, we get 0.061 negative 1.02 alpha. And since this is per radians, we specify that anyone who used this equation, please substitute alpha in radians. All right. So this was an analysis problem. I'm given the entire airplane geometry and I'm required to determine the moment characteristics. And from these two numbers, I can judge whether the airplane will be stable or not, whether it will have a good balance or not, right? But sometimes, okay, you as a designer, you're given the wing characteristics and you're required to design a tail to make the entire airplane satisfactory, right? This is the typical problem. So we're gonna have this problem now. This is actually, again, in the lecture notes, this is lecture 3. So here, all right, here is, okay. So this is the problem. So what's the problem? We're given the wing and fuselage together. I mean, in this course, we're really neglecting the fuselage, and it's a fair assumption, but sometimes the fuselage contribution becomes significant. At any rate, I mean, after this course, if you want to go and read these couple of pages in the book about the fuselage contribution, if you ever needed it, that it wouldn't be difficult at all. But we're trying to focus on the more important things. So at any rate here for this problem, we're given the two contributions together, the wing and fuselage. Fuselage, I mean, which is the body of the airplane. So this is the delta wing and fuselage, as you can see, of the CMCG. So as you can see, the CM note is negative, so which is not good. We want it to be positive. And you can see the CM alpha, yes, is negative, but it's weak. So we need it to be larger. At any rate, is giving you some area of the wing, aspect ratio of the wing, chord wing, CL alpha of the wing and fuselage. So you don't need to waste your time computing CL alpha 3-dimensional. I wing CL node also giving you many things, and is asking you to estimate the horizontal tail area and the tail incidence angle. How large your tail should be, and how you're gonna place it on the airplane. How you're gonna set it at what angle. So it's really a design problem, so that the complete airplane has the full wing pitching moment characteristics. This is what I like to see. CM node that is positive, and CM alpha that is negative and strong enough. The wing is not giving me, the wing alone is not giving me what I want. So I need to design a tail to have what I want at the end. Any question about that, about the problem description, the story? And let's see how we do it. All right, so how are we going to approach the problem? Like I always try to advise, probably one of the most difficult tasks in engineering is what we call the problem formulation. What do you mean by the problem formulation? Is that you are at your site, at your company, and you're given a story like this. And you need to turn this story into something that can be a homework problem, standard homework problem. Something like this is what we're used to in homework problem. Find X when Y equals something. Right? This is what we're used to. Find X when Y equals something. Typically, Y is a function of X. I equate Y with this given value, and I solve this equation for X. This is what we are used to. So let's turn this story into find blah blah, find some variable when another variable equals something. So when you are given the wing and fuselage here in red, when you're given the wing and fuselage characteristics, and you are given the total characteristics, right? So you're implicitly given what?
You're implicitly, oh my bad, bro, you go ahead.
The tail characteristics?
Yes, exactly. And how are we gonna get the tail characteristics from these two things?
You subtract the equations.
Very good. So let's subtract them to get the tail characteristics. So I'm gonna write down tail contribution of the CM is, please subtract these two equations from each other. So 0.15 minus 0.05, this is the 0.2, and negative 0.025 minus this number, you get negative 0.02, I guess, 15. Yes. He was saying something like alpha here is in degrees, so this is really degree. All right, so which means that this number is per degree. All right, so what do we call this? Do you have a, can you denote it? Is it something that we're familiar with?
CM not tail?
You're close, but it's not exactly CM not tail. I would say, oops, I would say, you know, it looks like a little bit pedantic, but it's not. So the tail, it's delta tail of the CM node, right? And what about this number? Any suggestion?
Delta tail CM alpha.
Exactly, thank you. Now it's becoming to be more crisp, the problem. Why? Because I'm required to determine the horizontal tail area, which is S tail and I tail. So I can actually formulate my problem now into this statement. Find S tail and I tail when delta till CM naught equals 0.2 and delta till CM alpha equals this number, because I actually have an equation for this guy, CM, delta till CM naught and delta till CM alpha. Actually, here are the equations. We can find them. Here are the equations, right? Maybe even down is better. Here are the equations. Delta tail CM naught and delta tail CM alpha, right? So I'm going to simply equate this equation with 0.2. Hopefully this gives me an equation for S tail and I tail, and the same here. Hopefully this gives me an equation for S tail and I tail, and I'm done. I'm gonna move this on a side now and just this start with this. So let's see what we have. So like I said, this is 0.2, right? Equals to a negative eta tail. I think it was given in this problem by Unity or something, no? Yes, assume, where is it? Assume the tail has the following values. Oh, it's not clear. Okay, let me get it again. All right. So eta tail is given actually, it's 1. I'm gonna write here 1. EH, as we know, it's S tail L tail over SC bar. S tail is my unknown. L tail is given 0.75 feet. Over S, here's S, 178. C bar, here's C bar wing, which is 5. CL alpha tail, it's given. I don't need to waste any time. So this is 0.073 per degree. All right. 1 minus d epsilon by the alpha. 1 minus d epsilon by the alpha. I need to get the d epsilon by the alpha and come back to solve this equation in S tail, right? Because S tail is my unknown. So to get it, this equation should have everything except my unknown. So d epsilon by the alpha is not ready. I need to go and get it. And luckily we have an equation for d epsilon by the alpha. D epsilon by the alpha is 2 CL alpha wing over pi aspect ratio of the wing, and everything is given. CL alpha wing here is 0.07 per degree. This is per degree. Over pi aspect ratio of the wing. Aspect ratio of the wing is 7.3. So here in this equation for the epsilon values, we really need to be careful. So this is why in the epsilon stuff, it's always recommended to have it the radians. So I'm going to multiply this by 180 over pi. So the result of the epsilon by the alpha is what? 0.35. I'm going to take this down even more. Jeez. I know what's happening. Let's see. All right, all right. What's happening? Okay, okay, anything. All right, just to clear. ratio of the wing. I'm going to do a similar equation for epsilon naught. It's 2CL naught wing over pi aspect ratio wing. This is 2. CL naught wing is 0.26. Pi aspect ratio wing 7.3. So whatever I get here, it will be in radians. So it will be a number in radians. I'm going to multiply it by 180 over pi if I want to write it in degree. So this will be 1.3 degree. This is the value that I was waiting here, 1 minus d epsilon by the alpha. So this is 0.3. As you can see, this equation now, what's the only unknown in this equation?
Professor,
Yes.
so for the tail contribution CM alpha, why is it 0.2?
Oh, thank you. It's not 0.2. Thank you so much. It's actually the other number. Other number, which is negative 0.0215. The tail contribution. This is the CM alpha. Thank you. Delta tail CM alpha is this value. So what is the only unknown in this equation?
ST.
ST. So I got the area, and here. So I'm glad this discussion. So you got now the sense that it's really the area of the tail that affects the CM alpha, the stability. CM alpha is the stability parameter, right? So you make it larger, and it's linear. Look at this, it's linear. Simply you increase this thing, this is increased. So the area of the tail, the necessary area of the tail is around 27.3 feet squared. This is what is required. So I got S tail to adjust CM alpha. Now, this was not the only requirement. The other requirement was the incidence, the I tail. Any suggestion? How should I do it?
Sorry, Professor, I have a question.
Yep. Yeah, sure.
How come the 0.073 value is per degrees and not per radian?
Let's see. That's that's a very good question. We should have paid attention to this detail. So the left-hand side, is it? So I wrote it like this, but does it have a unit or not? The left-hand side is CM alpha. Does it have a unit? Any suggestions, folks?
No.
Can you think about it again? Let's see. So CM alpha is a CM over alpha, right? So it's CM doesn't have unit, but alpha has unit, which is radians or degree. So CM alpha always have a unit, which is per radians or per degree. So when I see it like this is the value that is multiplying alpha. And I asking myself, when we are given this figure, the provider of the figure will always tell you alpha in this figure should be either in radians or in degree. So here it says that alpha should be in degrees. And if alpha should be here in degrees, it means that its coefficient is actually per degree. So this is the value that is per degree. This is per degree. And actually, for consistency, if the left-hand side is per degree, the right-hand side must also be per degree. So it was naturally with us per degree, but we always should pay attention to these details. So we're consistent, and S tail is okay. Everything is okay. All right. Questions?
Sorry, can you repeat again, like why the given function is per degree?
Why? Because here is the figure. It says here is the curve. It says the wing fuselage pitching moment characteristics of this airplane are, like this is the equation. Look at this, where alpha is in degrees.
Oh, I see. Thank you.
Yeah. Any question about that? So we got the area of the tail to adjust CM alpha, the stability parameter. And still we need to determine I tail. Any suggestion? How should I move? So simply, I mean, typically we have two numbers, the CM alpha and the CM naught. I used the CM alpha, I adjusted it by adjusting the area of the tail. I didn't touch the other number. So I'm gonna now go and write down an equation for this guy, delta tail CM naught, equate it with the 0.2, and hopefully this will provide me an equation for I tail. So here is delta tail CM naught. This was eta tail VH, sorry, VH CL alpha tail epsilon naught plus I wing minus I tail. This is the number that I need to make sure that it should be 0.2. Eta tail is given. VH is now ready because I got the S tail. Let's write it. So here is S tail. L tail, which is 14 point blah blah. Area. C bar. CL alpha tail. CL alpha tail is 0.073 per degree. Times epsilon naught. Luckily, I was preparing epsilon naught. Here is 1.3 degree. I wing minus I tail. Let's see what is I wing. I wing is 2 degrees minus I tail. Question here? Yes, thank you. So, any suggestions of modifying this equation, adjusting it, or it's ready, so it should proceed? Let's see. Left-hand side is CM naught, so this is non-dimensional, fine. Eta is non-dimensional, VH is non-dimensional, CL alpha is per degree. These guys are in degrees, so I'm okay. Per degree times degree is okay. And the only unknown in this equation is what?
It's just I.
It's I tail, and when I got it, it will be in what unit?
Degrees.
Degree, exactly, because it was simply added to degrees. So this is I tail. What will be typically it's at negative, and we're gonna know why. We typically locate the tail at a negative angle of attack or at a negative incidence. So I got, so as a flight mechanics designer, you have this as these two at your disposal, not with complete freedom, but with some freedom to size the horizontal tail area. It will be your job, it will be your responsibility to size the horizontal tail area, right? To make sure that you get enough stability. And probably this will be more freedom here as to, okay, how you gonna sit it on the airplane, the sitting angle of it, to ensure a good balance. And you can see I tail really adjusts CM naught, so adjusts the balance. S tail really adjusts CM alpha, so it adjusts stability. Any question about that?
I have a question on why I tail is negative.
On why what? I'm sorry.
Why I tail is negative.
Oh,
or just a small.
It's just
thing about that.
Do you mean why from the flight physics or why from this problem?
Oh no, like I was just wondering, is I tail negative making that negative on the equation like turn to a positive,
yes,
or is
yes.
Okay.
Yeah,
Okay,
when you
thank
compute it out of this equation, it will come out naturally negative. So yes, if you plug it back again, this will be positive, and yes, exactly. Yeah. All right. So let's now talk about a very important topic, which is the neutral point of the airplane. So the CM alpha of the entire airplane has two contributions, one from the wing, which was CL alpha wing XCG minus X aerodynamic center wing over C bar, plus another contribution which is coming from the tail. Sorry, this is negative, of course, it's a big mistake, right? CM alpha is negative and the tail contribution is negative. So eta tail VH, which is S tail, L tail over S C bar. This L tail is nothing but the distance between the CG end and the aerodynamic center of the tail. Times CL alpha tail 1 minus D epsilon by the alpha, all right? And this is CM at the CG, right? So the moment at the CG, this is the CM alpha part of it. Okay. So I can use this equation. I can simply copy it. To write down the pitching moment characteristics at any point. So for example, I'm going to replace the CG with whatever point I like. So here, if I'm talking about neutral point, this is neutral point, this is neutral point, right? What is neutral point? Well, neutral point for the airplane is the same as the aerodynamic center for a wing. So sometimes we say, okay, it's the aerodynamic center of the airplane. Okay. And what is the definition of an aerodynamic center? Any suggestion? What is the definition of the aerodynamic center?
The point where there's zero moment.
Not exactly. It's close enough. It's the point at which
the moment is constant.
Moment is constant. Very good. Moment doesn't change at the angle of attack. And if the moment does not change at the angle of attack, the slope should be what?
Zero.
Zero. So it's the point at which this is zero. Sim alpha 0. All right. So in fact, I can put 0 here and solve this equation for the X neutral point, and we're done. We're going to do it in a different way that will give us some insight into the airplane flight mechanics. So let's subtract these two equations. If we subtract them, so 0 minus Cm alpha is, here is 0 minus Cm alpha at the CG, all right, equals, I'm subtracting the second line minus the first line, okay? So when you do that, this aerodynamic center goes away because it's the same here, aerodynamic center goes away. And I get here X neutral point minus XCG. And again, here I have something similar. So I get X neutral point minus XCG. So, but this is negative, negative, so it will be plus. So now I will have CL alpha wing from the left, and from the right, I will have eta tail. Like I said, it's negative, negative, so it's positive now. Eta tail, S tail over S, right? And CL alpha tail, 1 minus D epsilon by the alpha, this whole thing, times X neutral point minus XCG, I'm sorry, yeah, over C bar. And if you have a very good memory, you're gonna recognize that this is nothing but CL alpha of the entire airplane, which gives us a really nice equation. So the neutral point that you're interested in, the aerodynamic center of the entire airplane, it must have some good meaning. This is negative Cm alpha over CL alpha for the entire airplane. So if you're giving me the two figures, the two important figures that we started the lecture with, the lift characteristics and the moment characteristics, they are both linear in our region of interest, small angle of attack. Just give me the slopes, CL alpha here and CM alpha there. If I divide the slopes, I get how far the neutral point is from the CG. Okay, so this is a very important finding, why we're gonna see in a minute. Remember, sometimes actually we're getting, instead of CM versus alpha, sometimes we're getting CM versus CL, and it's also a linear curve with a negative slope. So if you look here, this is nothing but like CM alpha over CL alpha is nothing but DCM by DCL. So if you are given the pitching moment versus lift characteristics, which is a combination of the two figures above, so it's actually the slope of that figure. The slope of that figure is the difference between neutral point and CG. So let's see. So this is my fuselage reference line, and this is maybe my wing. Here is the aerodynamic center of the wing, and here is my tail behind. Here is the aerodynamic center of the tail. So the aerodynamic center of the entire airplane is somewhere in between. And it will be closer to the wing because the wing is the dominant lifting surface. So here is the aerodynamic center of the entire airplane. All right, which is the neutral point. So the neutral point is the aerodynamic center of the entire airplane. And where should the CG be for a stable airplane? Let's look at that. So remember that this is the x-axis of the entire airplane, starts from here. And we want CM alpha for the entire airplane to be positive or negative for stability.
Negative.
Negative, exactly. This is the main message from the entire course, all right? When you guys see it at Albertson's 2 years from now, I'm going to ask you about it. So CM alpha is negative, and this is another negative. So I have here positive numerator. And of course, CL alpha is positive, no doubt about that. So the right-hand side is positive for a stable airplane. So this means that this must be positive, which means that the neutral point, X neutral point, should be larger than XCG. So X neutral point, or the neutral point, should be behind the CG. So the CG should actually be somewhere here. And this difference is what we call HN. We call it static margin. This difference. This is the HN normalized by the cohort. It's very important. Why? Because the aerodynamic center is behind the CG. So this is positive. So this is positive. So CM alpha is negative. The airplane is stable. The larger this distance, the more stable the airplane is. So if the CG moves forward, the airplane is more stable. This should be always in the back of your mind. CG of the airplane moves forward, the airplane is more stable. CG moves backward, the airplane is less stable. If it coincides with the neutral point, so this is 0, so CM alpha is 0, the airplane is neutrally stable. If it goes behind the neutral point, the airplane becomes unstable. And this is critical. Why? So actually, the airplane characteristics is characterized by this distance. Let's look at that. So if the static margin, we already discussed that the static margin is 0, the airplane is neutrally stable. If it's around 0.03, the airplane has light stability. If it's 0.1, so this is good stability. If it's larger than 0.15, this is heavy stability. What do you mean by heavy? Well, remember, I mean, we want the airplane to be stable, but not too much stable. Why? Because if the airplane is stable, it will reject disturbances, correct? But the airplane will not distinguish between a disturbance coming from the air, which is a true disturbance, and a disturbance coming from the pilot, which is a desired maneuver. It will reject both in a similar fashion if it's open loop. All right. So this is why we don't want to design airplanes to be too much stable, in particular if they are fighter airplanes. In fact, some fighter airplanes are designed to be neutrally stable or even slightly unstable. what are the implications of that? This is very important. Why? Because look at this. Changing the static margin HN by 5% from 0.1 to 0.15 will change the airplane characteristics from one configuration or from one category to another. And what do you mean by changing the static margin by 5%? Well, the static margin is the ratio between this distance and the chord of the airplane. So if the chord is, say, 1 to 2 meters, it means that the 5% we're talking about translate to 5 to 10 centimeters. So this puts a huge demand on the weight and balance folks, so that they adjust the CG travel. So the neutral point of the airplane is an aerodynamic characteristic. It will not change during flight. All right. It's like the aerodynamic center is at quarter chord. It will not change during flight for a wing. For the airplane, the aerodynamic center is here. Okay, we got it. So it's a fixed point. What about the CG? The CG changes during flight. Why? Because we lose weight. We lose tons of weight. The airplane uses between 30% to 50% weight, half of its weight, or 30% of its weight. So the CG will travel, and this puts a huge demand. Despite of this huge loss of the weight, the CG must not travel much, so that the static margin should not change within 5%. Questions? Questions?
So, okay, real quick regarding like a canard fit stabilizer, would the contributor of the CM alpha be a positive?
Yes, very good. Yes, exactly. The canard will give you a positive CM alpha. So the canard is typically unstable configuration, and you will need a flight controller to stabilize it. It will not be naturally stable. Yes, you're right.
And in addition to that, you wouldn't have a downwash.
Yes, you will have an upwash.
Okay. All right. Thank you very much.
You're welcome. Any questions? All right, guys, I'll release the homework right after this lecture, and I will see you in a couple of days.
Why is the homework due?
It will be due Friday midnight.
Okay, thank you.
This Friday midnight, right?
Yes, it will be like a couple of problems, not too much.
Okay, cool. Thank you.
You're welcome.
Thank you, Professor.
Thank you. Bye-bye.
Professor, take care.
Thank you. Bye-bye.
Actually, I had one follow-up question about the homework assignment.
Sure.
I like to use MATLAB as sort of like inputting my equations and stuff like that. So obviously, like I'll show work, but like,
yep.
That's totally okay, right?
Sure. Yeah.
Okay.
Mm-hmm.
All right. Have a good one. Thank you.
Bye-bye.
Thank you, Professor.
Thank you.
Professor?
Yes.
I noticed that on Canvas there's a new tab for the Zoom link. But
Yeah.
I think the link that shows up there for the lecture link and the link that you sent out in the email are different.
Oh no, it's just a second. This is, I think, for the discussion session. I think probably you have received a message on Canvas from the TAs about discussion sessions. I think this is the Zoom link for it.
Oh, okay. So this is only for discussions. Okay. Cool. Thank you.
You're welcome. Any other questions, folks?